Hi everyone. Welcome back to MP Coding. Today, we're moving on to the next method of synchronization primitives in FreeRTOS, direct-to-task notifications. In the previous videos of this series, we've already explored several synchronization methods in FreeRTOS. If you haven't seen them yet, make sure to check those out to get a better understanding of how synchronization primitives work. So, what makes direct-to-task notifications special? They are lightweight, fast, and don't require any additional objects like semaphores or event groups. Each task has a built-in notification value that works like a private semaphore or mailbox. Tasks can block and wait for notifications, and these notifications can be sent either from another task or from an ISR. This method is often recommended instead of binary semaphores whenever possible, because it's faster and more efficient. Alright, let's jump into the example and see how it works. As usual, I'll be using the STM32F429i Discovery board for this tutorial. Give a name to project and click Finish. First clear the default pin configuration. Then set up the RCC clock. For the middleware configuration, the FreeRTOS interface is set to CM-sys-v1. Here in the RTOS configuration parameters, you can see that the default use of task notifications is already enabled. So, we don't need to change anything here. Next, as before, I'll be using UART1 as a virtual COM port, so I'll set it to asynchronous mode. These pins will be configured as GPIO pins and connected to the logic analyzer. For the ISR, I'll be using the onboard push button connected to PA0, and set it as a GPIO external interrupt. If you've been following this series, you probably already know these settings. Then, go to the NVIC, enable the external interrupt, and set its priority to 7. I've already explained why we use this priority level in my previous videos. And finally, in the system time-based source, switch to another hardware timer. That's all, let's generate the code. For direct-to-task notifications, we only need to include two header files, freertos.h and task.h. So let's copy these includes, and in main.c, remove the cm-sys-os.h header, then paste the new headers. Next, I'll quickly remove the other pre-generated code, just like in the previous videos. I've already written the code, so let's take a look at it. Here, I've created 3 task handles and defined 3 task functions. In the main function, I created 3 tasks, with task 1 at the highest priority, task 2 at medium priority, and task 3 at the lowest priority. Finally, I started the scheduler. In the task 1, inside the loop, toggles GPIO pin 13 to indicate that it's running, then sends a message through UART. After a 2-second delay, it uses xTaskNotifyGive function to send a notification to task 2. And toggles PG13 again to show the notification has been sent. Before repeating the cycle, it waits for another 2 seconds. In the task 2. Here, the task first waits for a notification, using UL-task-notify-take. I've set the first parameter to PD true, so it clears the notification on exit. The second parameter is port max delay, so the task will block indefinitely until it receives a notification. Once notified, task 2 toggles PG14 to indicate that it's running, then prints a UART message. After a 1-second delay, it notifies task 3 using xTaskNotifyGive. And toggles PG14 again to indicate that the notification has been sent. Then it waits for another 1 second before cycling again. In the task 3. Task 3 also waits for a notification. When it receives the notification, it toggles GPIO pin 11 and prints a UART message to indicate that task 3 has been triggered. Then wait 500 millisecond, then blinks the pin and again waits another 500 millisecond. Okay, let's run the code. Here you can see that all the 3 tasks are running different time slots. Let's analyze this. Task 1 enters the loop first because it's the highest priority task. It toggles PG13, waits for 2 seconds, then notifies task 2, and toggles PG13 again to indicate that the notification was sent. On the logic analyzer, you can see that right after PG13 toggles, PG14 toggles as well. This means task 2 received the notification and started running immediately after task 1 went into the delay state. Task 2 then waits for 1 second and notifies Task 3. Exactly 1 second later, you can see PG11 toggle, showing that Task 3 has started running as soon as Task 2 blocked. This clearly demonstrates how direct-to-task notifications work in FreeRTOS. We don't need any extra semaphore or mutex, the notification mechanism itself is fast and lightweight. Now let's look at the ISR example. Here just one task that waits to be notified from an external interrupt. In the task 1, here UL task notify take blocks the task and waits indefinitely until a notification is received, and PD true means the notification value will be cleared on exit, so each notification only wakes the task once. When the task is unblocked, it toggles PG13 to indicate it woke up, sends a UART message. Then waits 1 second, toggles PG13 again, and goes back to waiting for the next notification. When the button press triggers the external interrupt, the ISR toggles PG14 as a quick visual indicator, and then calls vTask notify give from ISR to give a direct notification to task 1. The X higher priority task woken parameter lets the ISR know if giving that notification made a higher priority task ready to run. If it did, port yield from ISR requests an immediate context switch so the unblocked task can run as soon as possible. Okay, let's run the code. On the logic analyzer and UART you'll see the ISR toggles PG14 at the button press, then the task quickly toggles PG13 and prints, task 1, ISR notified. That confirms the notification crossed from the ISR into the task correctly and very efficiently. That's all for today's video. Today, we discussed a simple and efficient way to send notifications directly to a task using direct-to-task notifications in FreeRTOS. In the next video, we'll move on to another important synchronization primitive, message queues. So stay tuned, and I'll see you in the next video.